So there is a survey on your table that I want you to take. This is just to give me an idea of how you've worked in groups in the past and what kind of learning you're best at, so I can best organize groups. There's no grade attached to it. No penalty if you hate groups, no penalty if you love groups. Just be honest for me. We are going to start with wrapping up the discussion of Dalton, which I've got summarized up here. This isn't anything new. This is just what we finished on Wednesday. And then talking about the structure of apps. Tell me your name. Liv. And where's Liv's table? And then we're going to take the last part of class to go through looking at what evidence supports what claims, which is kind of a challenging thing to do, which is why we're going to work on it in groups first. My thinking had been that I would give you an assignment to do over the weekend. The timing in my first class made it look like that's probably, we're not going to be in a place to do that just yet. So if you wrote down that critical thinking about atomic theory is due Monday, I just changed that to Wednesday. So that is a new change. I would also like for you to read sections 2.3 and 2.4. We'll probably only get to 2.3 on Monday. 2.3 is how we describe the structure of the atom. How do we distinguish one atom from another? The vocab assignment isn't new. That's been up there for a while. And then homework 2, which is talking about all of these laws that we've been discussing, is going to be due Tuesday night in preparation for Wednesday. So make sure you're taking a look at that, because it says HW. That's the one that's on active chemistry. So you're going to have to go to active chemistry for that one. Vocab is just on Canvas. All right, so logistical questions. As I said, you should have all of this already in your notes. You don't need to rewrite this stuff, but you might flip back to that page where you were in the notes. We just kind of wrote down what Dalton said. So remember, Dalton is explaining laws of the time period, well, laws that we still hold through today, not the Constitution, not the Bill of Rights, but the law of conservation of matter, which is sometimes called conservation of mass, law of definite proportions, and law of multiple proportions. So theory explains this. So he's explaining, why are these laws true? Laws are just observations. We've noticed that this seems to always be true. Dalton says, I have an idea that ties all of these things together. So these are the different parts. And what I sometimes will ask on a quiz or a test is, what is he explaining with this particular piece of his theory? So first he says matter is made of indestructible, very small infinitesimal atoms. When he says indestructible, which of those laws is he addressing there? Is he addressing that matter doesn't seem to disappear, that we have different compounds, or that all compounds have the same formula? What do you think?
When he says indestructible, I believe that it's like they can be created or destroyed is what he means by that.
Exactly. Yeah, he's addressing this idea that we can't create or destroy things. Well, the reason we can't create or destroy things is because things are made of atoms which can't be destroyed. Okay, so this one addresses conservation of matter. Now, these two sort of define what an atom is, and we're going to skip over them for the moment, but basically they say one element has this mass and all atoms of that element have the same mass. If I have a different element, it has to have a different mass. It's going to look different, it's going to behave different. So then we get to number 4, and he says compounds are made of, so this is his definition of compound, 2 or more elements and that those two or more elements are a fixed number of each element. So for example, water is 1 oxygen and 2 hydrogens. All right, so is that addressing conservation of matter, definite proportions, or multiple proportions? What do you think, Hope? Okay, so conservation of matter addresses all matter, which is the ones that deals with just one
Oh, I
compound.
meant constant proportion.
Constant, yes, there we go.
I said that.
Yes, so this one deals with constant proportions. The reason why we have the same ratio oh, didn't realize I was doing that. Okay, I'm going to zoom out. The reason we have the same ratio is because of masses, is because we always have the same ratio of the elements. If every molecule of water is made the same way, of course we're going to end up with the same ratio of oxygen to hydrogen. Now this ties back to these up here because he was defining his atoms in terms of mass. So that's why he was explaining the mass ratio. And so these are connected to this. They don't really explain it, but they're connected to that constant proportions. Now, this sort of explains multiple proportions indirectly, because if in order to be water, you have to have 1 oxygen and 2 hydrogens, then if you have 2 oxygens and 2 hydrogens, it's no longer water. Okay, law of multiple proportions says if I have 2 elements, I can combine them in different ways and get different compounds. Okay, so this also explains multiple proportions, but it's a little more convoluted to get there. All right, and then the last one says in a chemical reaction, atoms are not created, they're not destroyed, they just get rearranged. So we've already gone through all of the laws, so we might have to repeat a law here. Which law does this sound like? Nothing's created or destroyed. Yeah, so this one's back to our conservation of matter. The reason why the mass stays the same, the reason why matter doesn't seem to be created or destroyed is because we're not destroying the atoms, we're not creating new atoms out of anywhere, we're just moving them around. Okay, so on my list here, I said, how does the theory explain the observations? That's what we just did. And now what I want to look at is, do we still accept this to be true? Do we still say, yep, Dalton was right, don't need to change anything? So he said a lot of things, so we're going to look at it piece by piece, and then think about what modifications we might make to make this more like what we would say today. So this first part says matter is made of indestructible atoms. So indestructible, we still agree with that? Sometimes we say indivisible. We still agree they're indivisible? We break an atom into smaller pieces? Can't break it into smaller atoms. It doesn't have smaller pieces. That have protons and neutrons and electrons. Yeah, so this one, so if there's a little asterisk up here, I'm going to put the asterisk down here and say, we now understand atoms have subatomic, sub meaning below, so below the atomic level. Try to write big here for you. So that's going to be our protons, electrons, or neutrons. And then if you get into particle physics, then you get into quarks and gluons and all sorts of other things, but we're not going to get into that stuff. Okay, so the next one says atoms of one element have identical mass. So would we agree today that all atoms of carbon weigh exactly the same as each other? No. What might be different? isotopes. So this might be a term you're not familiar with. We'll talk about this probably Monday, what isotopes are. But basically, we know that most carbon atoms weigh about 12. Some of them weigh about 13, some of them weigh about 14. So I have a little double cross there. I'm going to put that at the bottom. Atoms can have isotopes. Good word to know, with different masses. Right? And we'll get a better definition for an isotope next week. But basically, there's part of Dalton's law that, you know, it seemed reasonable at the time, but we now know it's not quite true. Okay? Do we still think that all carbon atoms have the same chemical properties? Actually, with the exception of hydrogen, pretty much this is still true. All carbon atoms chemically behave the same. Now, you may be thinking, yes, but carbon-14 is radioactive. That's a nuclear reaction. So nuclear reactions are kind of a different thing. We're not going to worry about those. Chemically, carbon-14 behaves the way carbon-12 does, which is why we can use it for radioactive carbon dating. That's another thing. Okay. So number 3 here, atoms of different elements have different mass. Do we agree with that? Carbon atom doesn't weigh the same thing as a nitrogen atom? Yeah. And there are some that weigh pretty close to each other, but they're going to have slightly different masses. What about the second part? We can't change from one element to another. This is kind of a tricky one because it depends on how much you know about physics. Sometimes elements can change. This is what happens in nuclear decay. So if you've heard of uranium, which decays, when it decays, it's no longer uranium. It becomes thorium, and that becomes radium, and that becomes radon. Okay, so I got a squiggly line there. In nuclear reactions, and remember the nucleus is where our protons and our neutrons are, which tell us what the atom is. In nuclear reactions, elements can change. Now, can you turn lead into gold? Not really. You could theoretically turn platinum into gold, but you can't really turn lead into gold, and platinum is just as precious as gold is, so in theory, it wouldn't be a lot of point. Okay, so with these last two, the things that we addressed with nuclear reactions, those are not chemical reactions and aren't really the scope of this class. So while we might remember, yeah, that's a little bit not true, for our purposes, they don't really matter. Right, so we might look at, and then these last two, these are pretty much still the same. We still think of compounds as 2 or more elements having a fixed number of atoms in each element. We still think that chemical reactions involve atoms rearranging and not being created or destroyed. We might look at this now instead of a theory because it's no longer accepted as exactly true, but it's a good model. If I were trying to teach a little kid about atoms, this might be a good place to start. They don't need to know about nuclear reactions. They don't need to know about isotopes. This would give them a good basis for understanding that matter is made up of little particles. Okay? So remember, a model, we might know there are mistakes, but they're not really important for what we're trying to do right now. Okay, so that's Dalton. Now we're going to switch gears and talk about these subatomic particles. All right, so we have up here Dalton. What was his idea of an atom? He kind of thought of them like a pool ball or a billiard ball, where it's this solid thing that you couldn't destroy, you couldn't break it up, and it was pretty uniform. He didn't think of it as having parts. This is the early 1800s. Now, just before the early 1800s, early United States history, one of our heroes of the US at the time was Benjamin Franklin, who is most remembered probably for flying a kite in a storm, right? So I don't know whether or not that's true, but we associate that with him sort of discovering electricity, that you can harness electricity and do things with it. So at that time, from the late 1700s through the mid 1800s, that was like the new toy for scientists, that they were like, oh, let's see what we can do with electricity. So microwave ovens came out when I was a little kid. And like everybody at the time, when we first got our microwave oven, we were like, ooh, I wonder what we can put in here. And so we would put bowls and we would put forks and we would put food, and hopefully nobody put in a cat, but we didn't have a cat, so didn't worry about that. But you quickly learn that like you can't put a fork in a microwave and expect it to, not damage the microwave or whatever. And so kind of imagine scientists at the time are like, ooh, electricity, let's see what I can zap with it. I'm gonna zap this, I'm gonna zap that, I'm gonna zap that. And so one of the things that they did is they put electricity through water and discovered that you could get gas out of it. In fact, you could divide it into two gases, one of which was very explosive, that turned out to be hydrogen, and one of which was not very explosive, but would help, say, a candle burn. Okay, and that would be our oxygen. They also ran electricity through salts. So table salt, what's that made of? Sodium chloride, so two elements, sodium and chlorine. Okay, they ran electricity through it, and this white crystal turned into a puddle of shiny silver, and then there was a green gas. Okay, we're like, what the heck? We can get chemical reactions to happen by running electricity through. And this is actually how they discovered sodium as an element. So prior to electricity, there really wasn't a way to find sodium or potassium separate in the environment. It didn't exist in piles on its own because it was so reactive. But by running electricity through things, they discovered several new elements. Okay, so that's the first observation, that, hey, we've got this electrical current that's doing something. We don't know what this electrical current is. And so they, among the other things that they did, they came up with these tubes called a cathode ray tube. And the idea of a cathode ray tube is instead of just running the electricity through a wire, you break that wire and you have a plate here and here. Okay, and so one plate is positive, one plate is negative, and the electricity will jump from one plate to the other. Okay, and then if you stick a hole in your second plate, sometimes when it's trying to jump to the second plate, it'll go through that hole. Okay. They then discovered that, hey, this can cause some things to light up, what we call phosphors, will light up, and that led to the development of televisions. So if you've seen an older television that's more like a big box instead of a flat screen, that's actually a cathode ray tube. It's exactly the same principle as what was being done in the 1800s. Old computer monitors were the same way. Let's see where am I? Okay, so here's a cathode ray tube, and I forgot I was doing this. Oops. There we go. Okay. So this looks a little bit different from how I described it. Our two metal plates are here at the end of the tube. The second one has a hole in it, and then anything that goes through that hole is going to go through this side. And this is where they would put like phosphorus and have it glow when the lights would hit up. And that's where like your TV screen. So there's a lot of, playing around with it, seeing what works, seeing what you can do with this. But J.J. Thomson gets credit for trying to understand what is this cathode ray to begin with. So it was called a cathode because it seemed to be coming off of the first metal plate, which they called the cathode. And that metal plate was negatively charged. And it would go towards the anode, which was positively charged. So a cathode, being negatively charged, told him, this probably has a negative charge. So let me see if I can test that theory. And so he put various things around his cathode ray. So the first thing that we're going to talk about is a magnet. That was known at the time that if you have a magnet, it can influence electricity. If you have electricity, it can influence magnets. So they influence one another. And so he said, hey, if I put a magnet around my cathode ray, it bends. It goes to one side or the other, or up or down, or whatever. So it's got to be made of charged particles. It's got to have some electricity associated with it. Yeah.
So with the magnet being on the cathode tube, is that why the old televisions would always have messed up colors when a magnet was brought here?
Yeah, exactly. Yeah, because it's the electrons that are hitting the screen, and so you're deflecting where they would go. Yeah. All right. So if you didn't hear the question, he was asking if you've ever seen an old screen like that, and you took a magnet to it, it would like mess up the picture as you brought the magnet towards the screen because you're moving around the electrons. Okay. So the next thing that he tried then was, okay, can I show that it's negatively charged? So he puts metal plates above and below where the electrode is, or the cathode ray is going through, and one is positively charged, one is negatively charged, and he finds that it always bends towards the positive plate. Okay, now what we know about charged particles, positive and negative, if it's going towards the positive, it's probably what? Negative, because opposites attract, right? So he says, since the ray bends towards the positive plate, it's going to be made of negative particles. I'm not going to go into how he figured this out. It's a little bit complicated, but he also figured out that they were very light particles. They weighed a lot less than any previously known atom, hydrogen. So he didn't think that they were like a new element. And then the last thing he did is he took this cathode and he tried different metals. He tried gold, and he tried iron, and he tried copper, and he tried silver, all sorts of different metals, and it always behaved exactly the same way. Not just that it would bend, but it would bend the same amount in the same magnet, or the same amount in the same electric field. So his conclusion was, whatever it is, it's not different in different elements. It's the same thing in different elements. It is part of all matter. Okay, so we've got something that is very tiny, negatively charged, and found in all atoms. What did he discover? Okay, so we've got both protons and electrons, and there are neutrons, okay, and they all have different charges. So neutron is neutral, proton, starting with a P, is positive, so he discovered the electrons. The E is negatively charged. All right, so this line just sort of summarizes that. We've got light negative particles, they're part of all matter. He discovered the electrons, okay? So I may ask you on a test or a quiz, what did J.J. Thomson discover? Or what did the cathode ray experiment, which is probably more important than his name, what part of the atom did it discover? And I'm just adding on to what I had before. So if you've already written down Dalton and evidence of something more, you don't need to write it again. I'm just adding on to that same thing. All right, so the next experiment is one that we kind of throw in here because it's sort of important, but it's not one we dwell on very much. So I'm going to talk about it a little bit, but it's not hugely important. So the cathode ray tube was developed in, you can see, right before 1900, around the same time that people discovered X-rays. And we'll talk about X-rays in just a second here. Millikan did his experiment right after 1900, but before World War I. And so his experiment involved oil droplets. And so kind of like early on, they were zapping everything with electricity. The new toy around 1900 was the X-ray. So now they're zapping everything with X-rays. So he's zapping these oil droplets with X-rays. They knew that if they did this, they could get a charge on the oil droplets. And so he's kind of messing around with that. So we've got this thing up here, kind of looks like a perfume bottle. That's exactly what it is. It's called an atomizer because it creates very tiny, tiny particles. So they're not atom size, but tiny particles. And so you get this mist of oil droplets and they all drift down, and some of them make a mess on this plate here, but some of them go through this hole, okay? And so the ones that are going through the hole, he knows are going straight down rather than going at an angle, because he had to go straight down to get through the hole. And then he's gonna shoot his X-ray at these things. And this plate and the one below it, he can put a positive and a negative charge on it. He can increase and decrease and try to get that particle to kind of hover in the middle, okay? So by figuring out how much energy it takes to get it to hover in the middle and the weight of the oil particles and all of that, he discovers what, and he's looking at it, if this is him over here, it kind of looks like it was. So he's watching through here, making it hover in here. He figures out the charge on each particle. And so sometimes the charge, he's measuring this in coulombs, sometimes the charge is 1.6, and sometimes it's 3.2, and sometimes it's 6.4, but it's never 2.3 or 2.5 or 1.7. It seems to always be hitting these same numbers, and all of those numbers are multiples of the smallest number. And so from that, he decides that we must have the same charge on all of these electrons. So you might think, well, yeah, duh, each electron is -1. But it wasn't really obvious to them at the time because we're still kind of lingering through that whole, we just discovered matter's made of atoms. We had thought of everything as being continuous. So the idea that not every electron would have the same charge didn't seem incongruous to them. But that's what he discovered. And now you also might be thinking, wait a minute, what's this 1.6? I thought it was a -1. So this is like the difference between inches and meters. So coulombs is the charge or the unit that we use when we're talking about a lot of electricity. What we do when we're talking about electrons is we put them in atomic units because scientists like to take shortcuts. And so we just say -1. So it's -1 unit of it. Okay, so he found that the charge was always some multiple of this. This number is not important. You don't need to know that. But what he discovered was that electrons all have the same charge. That's the important part. And again, the top part was already there. You don't have to recopy the top part. Just adding on. All right, so the next one, the last one we're going to talk about is Rutherford's gold foil experiment. This one is really kind of key to our understanding of atoms. And so the name Rutherford, also the name Thomson are important to know and what they discovered. Millikan, it's important to know that all electrons have the same charge. We won't really come back to him. Okay, so what did Rutherford do? Rutherford was a scientist from New Zealand, worked in Canada, worked in England. He moved around a lot. Okay, so first, what did he think prior to his experiment? This is kind of important because this is one of those examples of what he was trying to show didn't work. And so he had to revise his theory. And so after Thomson, the idea was, okay, we know we have these little negative electrons and things, these little negative particles. They're probably just like embedded in the surface of this positive stuff. So there's a positive thing with lots of electrons attached to it. That's an atom. Okay, so that's what you see over here. This is what they were thinking that was. They called that a plum pudding model. And so that was his thinking. And knowing the density of matter and things like paper and clothing and things like that, it was like, okay, yeah, the spread out, the mass is spread out throughout this. So if I can shoot something through there, it should go through any one part of the atom as easily as any other part of the atom. There shouldn't be one part that is different, is basically that. Now, cruel fact of the matter is that when somebody has a PhD and they're doing their research, they're not actually doing the research. They usually have a PhD or a postdoc or a graduate student, sometimes undergrads, that are doing all the work for them. And then they write the paper and get the credit, maybe give a little bit of credit. So he has a grad student named Geiger. Okay. So his experiment is he wants to take these newly discovered alpha particles, so kind of like electrons, they're tiny little charged particles, but these are positive. They only seem to come from things like uranium and thorium, so it doesn't seem to be in all matter. He's kind of testing them, and he wants to see what can they go through. Can they go through a sheet of paper? Can they go through a block of wood? And in this experiment, he's testing how much gold does it take to stop it. And so he's got his source of alpha particles here being shot through the gold foil, and then when it hits this thing over here, it lights up. Okay. And so he tells his student Geiger, your job is to turn this on and count how many times you see it light up over here. So if you've ever heard of a Geiger counter, it is named after Geiger, whose job was literally to count how many times the radiation showed up here. And so he did, dutifully. But as I said a week or so ago, it's important to notice things. And he noticed that aside from getting almost all of the flashes here, every once in a while you would see them to the side. And even more rarely, he would see some of them bounce backwards and hit in the back. You would see little flashes of light back there that meant radiation. So of course, Rutherford said, no, you screwed it up, you did it wrong, set it up again, do it again. This went on for a while. And finally he said, you know what, I think we've got something here. So he revised his theory because this model did not support things being shot backwards. Okay, so why was he surprised? Think of the alpha particle like a bullet being shot from a gun, and the gold foil as a sheet hanging on a clothesline. Okay, if you're shooting a gun at a sheet, you expect that bullet to go through the sheet. You're not going to like tell your best friend to stand behind the sheet because they could get hurt, right? That's what he's expecting all along here. So if one of those bullets had bounced back and hit him, he would have been pretty darn surprised. And that's why he didn't believe Geiger at first and why he's very surprised about this, okay? So now let's think about this sheet hanging in front of a chain link fence. Okay, so most of the time, if you're firing at that sheet, it's going to go through one of the big holes in the fence, and it's just going to behave as normal. But every once in a while, it might hit the link, in which case it might bounce back or go to the side or something like that. Okay, so his idea is that rather than the mass of the atom being all spread out, it's all concentrated in one very small area. Okay, so he says, it has to be a really small area because this doesn't happen very often. Most of the time, it's just going straight. It's like 99.999% of the time, we're going straight through, and like 1 in a million times, it's bouncing back. So it's got to be teeny, teeny tiny. But then how do you explain these things, where it's just going slightly to the side? So he said, I know alpha particles are positive, and I know if I get two positive things right next to each other, what are they going to do? They attract it or go apart? They're going to go apart. So I've got this positive thing coming along. It sees the positive thing, and it goes to the side. So he says, I think this deflection here is because whatever this really dense, small thing is also positively charged. Okay? So we've got something very tiny, something positively charged, not taking up much space in the atom. What do we got? That's gonna be the nucleus. So sometimes people say, well, it could be the protons, but they hadn't gotten as far as protons yet. So at this point, they're just thinking big positive ball, not really thinking of that as hepatocytes. That comes later. We're not gonna worry about that. But we have this going on here. Okay, so we have a positive charge concentrated in a very small dense area. We have a nucleus. Okay, so we're going to take a look at this first thing where it says in this exercise, you're going to be connecting evidence collected to claims that this evidence should support. So on this page, which you're going to turn in before you leave today, this is all stuff we just talked about, okay? I'm hoping to give you time to look at some evidence of the stuff that you're going to be using for the critical thing. We'll also look at that on Monday. Okay, so it says the fact that cathode rays deflect towards positive electrodes shows that what? So next table, decide what you think deflecting towards a positive electrode tells us about the cathode ray. The cathode ray goes towards the positive electrode. From that, we can conclude what about the cathode ray? All right, so one of the spokespersons, tell me, what did your group come up with? Go back here. What did you think of this? That it is a negative particle, okay? So that's the kind of thing that we're looking for. We know that it's negative because it was attracted to the positive, okay? So the connections I'm looking for are not, I'm not trying to get real convoluted here. I realized last period that the question that I asked for number one was a little bit more convoluted than I was trying to, because it's not about evidence. So it's like trying to have you do something else when I just said I was having to do this other thing. So just as a frame of reference, what did Rutherford expect about the mass before his experiment? Did he expect it to all be in one place, or did he expect it to be spread out? He expected it to be spread out. So that's what you can write down for the first one. Rutherford expected the mass to be spread out. So now what I want you to do is take about the next 5 minutes and talk about 2, 3, and 4. What are we showing about, and all of these are Rutherford, so what do we know about the nucleus based on this evidence?